All right, this is going to be our video all about torque and angular acceleration. So we already know that we can calculate torque by doing the force applied times the distance from the axis of rotation times the sine of theta. And we know that if an object has a net torque, then that leads to rotation. But we need some way to quantify that rotation. Okay, so we can kind of think of like net torque as the net force of rotating objects. We know that when there is a net force acting on an object, they move linearly. So we know there's a net torque on an object, they rotate. So maybe we can use that to kind of come up with something. So we know that if there's a net torque, we can quantify that movement with a linear acceleration, or what's sometimes called a translational acceleration. So we need something to quantify torque with. Well, maybe we quantify it with an angular acceleration. And that angular acceleration is going to be the rate at which rotation increases or decreases, right? If we have a net torque in the same direction as we're moving, the object should speed up rotating. If our net torque is opposite the way we're moving, the net torque should slow down. Okay, so again, we're using this kind of comparison between net force and net torque to get at that we should quantify the amount of rotation that a torque produces with something called angular acceleration. So angular acceleration is represented with the Greek letter alpha. Yes, it looks very similar because it is the same thing as our proportionality symbol, so it's up to us to kind of differentiate between the two, just like J for impulse and J for joules. Based on the context, we can figure it out, and the units are radians per second squared. So if an object has a net torque, it will experience this angular acceleration. So now you might be wondering, what the heck is a radian? Right, so since we're talking about rotating objects, we're not going to measure that rotation in meters because something can't rotate 5 meters, but it can rotate through a specific angle. So that's what a radian is. A radian is a measure of circle completion or an angle. And if you're in pre-calc or even algebra 2, then you are very familiar and probably hate radians, and that's okay. But one rotation, so if we rotate once around in a circle, that would be considered 2 pi radians. Half a rotation would be considered pi radians. So how then is torque related to alpha? We know that there's a direct relationship between net force and acceleration, but is that still true with net torques and acceleration? So we're going to do a little simulation and take some data. I'm going to look at the net torque acting on a spinning turntable, and I'm going to measure the resulting acceleration. Okay, and basically what I'm going to do is I'm going to start with one torque, and then I'm going to double it, and I'm going to see what happens to the acceleration. We're going to do a couple of iterations of that. So the simulation I'm going to be using is a FET simulation, and to get to this you can just Google torque FET and you'll see this pop up. And if you want to run it in your browser, you use some weird thing called ChirpJ. I don't really know what that is, but I am currently in the moment of inertia tab. We'll talk about what that is later. But basically what I can do is I can change the applied torque, and then I can see the resulting angular acceleration. Now I could also add a brake force if I wanted to create a sort of like net torque. But for now we're going to ignore the braking force, and I'm just going to have a net torque. So my first torque that I'm going to apply is just 1, and torque is measured in Newton times meters, that's force times distance. So I'm applying that torque, and I can hit go. And yay, it spins, and then when I hit stop, there we go. You can kind of see there is my line for my net torque. It's a little bit small. You can't really zoom in. There we go. right? It's that green line right there. So let's see what the acceleration is. All right, the acceleration is 1. What I'm noticing also is that the acceleration of the ladybug is also 1. So the ladybug is on the platform. So right now it looks like the platform and the ladybug have the same angular acceleration. I'm going to move the ladybug. Oh no, stop. Okay. Oh, well, I moved the ladybug and they still have the same angular acceleration. So what that tells me is that no matter where this ladybug is, it'll always have the same angular acceleration of the platform. Now, the reason why I have the ladybug on there in general is because it needs to be on there for the simulation to work. But it's a good thing to keep in mind that basically everywhere along this platform is going to have the same angular acceleration. And that makes sense because we're all spinning in a circle at the same rate. Okay, so let's go back to my data table. So I did 1 Newton meter of net torque, and that gave me 1 radian per second squared of angular acceleration. So now we're going to double that torque to 2, and I'm going to see what the resulting acceleration is. All right, so I have an applied torque of 2, and right, my angular acceleration jumped up to 2. Okay, so I doubled it to 2 Newton meters, and this also doubled to 2 radians per second squared. So far, looking like a direct relationship. Let's triple it, right? Because if I triple the net torque, and if this is a direct relationship, the angular acceleration should also triple. So we'll let that go for a little bit. All right, let's adjust my graphs. All right, so there's my net torque at 3. And when I come down here, I have an angular acceleration of 3. So we could keep doing this pattern where we're doubling or tripling the net torque, or quadrupling, or however many timesing. Oh, I guess, I didn't triple it. I just made it 3. All right, so now I'll triple it. I'll make this 9. That was silly of me. All right, so 9. All right, let's zoom out. Right, I know it's written up here, but it's cool to see the graph too. So that's 9, and we can see that our acceleration is up to 9 too. So I'm pretty confident at this point that I can satisfy or say that this must be a direct relationship. So I can say that the net torque is directly proportional to the angular acceleration. So it's probably, our equation's probably not going to look like net torque is acceleration, because if I change anything about this platform, like let's say I change the platform mass to, I don't know, I'll make it really, really big, right? And I still apply that same torque, right? The angular acceleration changes, and I don't know, I could change the outer radius, right? So it was 4.5 when I changed the mass, right? Now it's 8.85, so that outer radius matters, and then I could change, I don't know, whatever, that kind of like makes it a hoop. Change that inner radius. All right, now my angular acceleration is 5, and the ladybug fell off. Right, so what this tells me is that, you know, the angular acceleration isn't exactly equal to the torque. That was just how the numbers were set up. That tells me that there must be something else, some sort of constant that relates net torque acceleration. So my equation probably looks like net torque equals something times alpha, right? Kind of like net force is based off of m times a, right? The m is the constant, right? Like if I increase the mass and have the same net force, then acceleration decreases. So there's going to be something that is very similar with net torque, and that thing is going to be called rotational inertia or moment of inertia. we'll most often use rotational inertia, right? Just like mass is sort of like a measure of linear inertia, right? How resistant something is to changing velocity. Okay. So we're going to talk about that idea of rotational inertia or moment of inertia in another video. Now, one thing I want to bring up is let's go back. Let me reset everything. Clear. Yes, I want to reset everything. But this time I am going to show some of these linear vectors. I'm going to show my linear velocity vector for my ladybug. I'm going to show my acceleration vector for my ladybug. Okay. So I'll apply a smaller torque of 4, right? And now let's watch. So initially, my velocity vector is kind of pointing perpendicular to the rotation. And if we think back to circular motion, that makes sense. Something moving in a circle has a velocity perpendicular to the rotation. But this acceleration vector is not pointed directly inward like we might expect. So even as it speeds up, still not pointing directly inward. We're kind of off at an angle. Okay, and that's going to be because we're not moving at a constant speed. So not only do I have a centripetal or inward acceleration, we also have something called a tangential acceleration. That's all I'm going to talk about with regards to that now. I'm going to give you guys a flipping physics video to watch that'll kind of explain the difference between all of these accelerations that rotating objects experience. But for now, point of this video is we're seeing that torque is directly proportional to angular acceleration, or as a lot of students affectionately call it, fish. And that's it.